So our next speaker is Saeed, and he's going to talk about approximation algorithms for longest common substring and longest increasing subsequence.
Thank you. This is a joint work with Aviad, Rubinstein, Zhao, and Xiaorui. I'll be mostly talking about LCS, but I'll say a few words about LIS as well. OK. So in LCS, you have two strings, and you want to find a subsequence which is shared between them, and the length of this subsequence is maximized. To clarify, in a subsequence, we allow for gaps, but in a substring, we don't allow for gaps. So here, we are concerned with subsequence. The problem is old, and the solution is not very hard. You can solve LCS in quadratic time with dynamic programming. Can we do better? Many people ask this question. Thus far, we don't know. Actually, there is good reason to believe that we can't, because Abbott, Backers, and Williams show that if you come up with a faster algorithm, substantially faster algorithm, then a strong exponential time hypothesis is refuted. There are two closely related problems. One of them is edit distance. There are many different variations for it. One variation, which is the relaxed version of edit distance, is exactly the complement of LCS. So instead of finding a subsequence that is shared, we want to remove some characters such that whatever remains in the strings is the same. Now, if you want to find an exact solution, then the two problems are computationally equivalent. If you want to get approximate solutions, that's not the case. This situation is the same for like maximum matching versus vertex cover. The other related problem is LIS, or longest increasing subsequence. You have an array of lengths n. You want to find a subsequence whose values are increasing. Why is this a special case? Because if the string has two permutations, or if the problem has two permutations or two strings with no repetitive characters, then the problem is exactly equivalent to LIS. LIS is much easier to solve. We can do it in linear time, but LCS requires quadratic time. There is literally a ton of work on these two problems. These you see on the screen, these are just linear time. There's sublinear time, subquadratic time, beyond worst cases, smooth algorithms. There's a lot of work on these two problems. For linear time solutions, much progress is made for edit distance. The latest we know is due to Andani, Onak, and Kartkamer. They give polylogarithmic in linear time. For LCS, there is some improvement, but we just know how to break the trivial bounds. Like, you can get root n approximation in linear time. There is a recent work that gives n to the 0.498. It improves the exponent a little bit. Or there's another trivial solution that just counts the number of characters. It gives you sigma approximation when the alphabet size is sigma. Recently, this bound is improved by Rubinstein and Zhao. In this talk, I'm not concerned with linear time solutions. I allow the runtime to be as large as n to the 1.99. Basically, I want to be just better than quadratic. Now, if you're following these two problems, you should know that there was a great breakthrough recently for edit distance. It was a long-standing open question whether we can get constant approximation or not. A few decades ago, people started to believe that we can, but we didn't know how to do it back then. The problem is solved last year. Now we know that we can get constant approximation for edit distance. Our work is about LCS, and we give the same solution for LCS. So the runtime for LCS is subquadratic. The approximation factor is not constant. It actually depends on the size of the solution. So I don't tell you what exactly it is. I'll tell you at the end of the talk. I just say that it depends on the solution size. If the solution size is large, then it's small. If it's smaller, then the approximation factor deteriorates. But I'll tell you that this is exactly the dual solution for LCS. To begin with, both these two solutions are based on triangle inequality. Now, triangle inequality is simple for edit distance. You have three strings x, y, z. You know the edit distance between x and y is alpha. The edit distance between y and z is beta. You just can imply that the edit distance between x and z is bounded by alpha plus beta. It is not easy for LCS. You can think about it yourself. So suppose you have LCS between x and y alpha, between y and z beta. It's not clear what kind of a lower bound you can get for x and z. And it's a cool problem to think about. I'll tell you what we can get, but later in the talk. Now, our algorithm for LCS is inspired by the same solution for edit distance. This is given by Chakrabarty et al. They have this framework that has 3 steps. If you combine all these 3 steps together, then you get a constant factor approximation. One thing to note is that a similar framework was previously used to get a quantum solution. Previously, in one of the steps, they used a search from quantum machinery, and because of that, the algorithm was quantum. I'll briefly tell you what they do in each of the steps. For one of them, I actually go in detail because much of what we do depends on previous work. So in step 1, what they do is pretty similar to a reduction. You have 2 strings, and you want to estimate the edit distance. They're going to divide the strings into smaller pieces. I'm going to call them windows. It turns out that if you know the edit distance between the windows, you can figure out what's the edit distance between the strings. So really the question is, what are the edit distances between the smaller windows? They make a graph from the windows. I'll tell you how exactly they make it. But then the question becomes, what are the edges in this graph? They discover the edges in 2 steps. Step 2 handles the case that the graph is dense. For that, they use triangle inequality. And step 3 takes care of the case that the graph is sparse. So for this talk, I'm going to skip step 1 and step 3. I'll just tell you what they do in step 2. And then I'll tell you how we change it to get a solution for LCS. All right, so at this point, we have a bunch of windows. And the goal is to find out what are the edit distances between the windows. I want to make a graph. So I define a threshold delta. For every window, I introduce a vertex. And if the distance between 2 windows is bounded by delta, I assume there's an edge. For fixed delta, if you tell me what are the edges, I can figure out which pair of windows have a distance bounded by delta. It's not hard to find out that if you do this for a small number of deltas, you can figure out what are the edit distances. So really, the problem is to find out what are the edges of the graph for a fixed threshold. OK, so there's a stupid algorithm for every pair of vertices. Just compute the edit distance and verify whether there's an edge or not. We don't want to do that, because if you do that, the runtime is going to be quadratic. What we want to do is that we want to spend less than edit distance time per edge. And keep in mind that the graph is dense in this step. So we first find an edge. It's not hard to do that because the graph is dense. So we sample a bunch of pairs. One of them has an edge. For the 2 endpoints, we're going to compute the edit distance of these 2 strings from the rest of the windows. This way, you can list all of their neighbors. But up until this point, we spend edit distance time for every edge, so we don't save anything. But here is how we save. You can imply by triangle inequality that the edit distance between left windows and right windows is bounded by 3 delta. So you don't need to compute the edit distance explicitly. You can just close your eyes, report all of them as edges of your graph. You will lose a factor of 3 because these distances are bounded by 3 delta. But the amortized time for finding an edge is better than edit distance time. So that's the whole point of improving the running time to subquadratic. You keep doing this. You keep discovering the edges until whatever remains in your graph is sparse. And then you use a 3rd step to discover the edges. All right, now going to our algorithm. This is inspired by the same framework. We have 3 steps. 2 of the steps are exactly the same, step 1 and step 3. The only step which is different is step 2, because they use triangle inequality to improve the runtime. We don't have that for LCS. So here is the conceptual contribution that we have. We give a new notion for LCS. We call it birthday triangle inequality, because we see this as a combination of birthday paradox and triangle inequality. The cool thing about this notion is that it doesn't always hold. It only holds on average. Now, going back to the problem. We have 3 strings x, y, z. We want to drive a bound for LCS of x and z. Instead of alpha and beta, I'm going to use multiplicative terms. So the first one is lambda L. L is the length of the strings. Lambda is between 0 and 1. The second one is gamma L. Gamma, again, is between 0 and 1. The thought behind the inequality is the following. Suppose I randomly sample one element of the middle string. With probability lambda, it's going to contribute to the first LCS. With probability gamma, it's going to contribute to the second LCS. If the probabilities are independent, and this is not necessarily the case, then with probability lambda times gamma, it contributes to both of the LCSs. So in that case, you can imply that the LCS between x and z is lower bounded by lambda times gamma times L. This is not always the case. That's why we call it that's why it only holds on average. If the first one only has A's, the second one only has B's, half A, half B, this is large, this is large, this is very small. But the way you can think about this inequality is the following. Suppose you have a set S of a lot of windows, and you randomly choose 3 of them. Then there's a good chance that you can use this inequality. There's a constant probability that the LCS between x and z is lower bounded by this expression. Now, we're going to use this new notion. We're going to replace it with triangle inequality. But then a lot of problems come up. Because this new notion only sometimes works. It doesn't always work. And that's a big challenge for making the algorithm, because we want to get an algorithm that gives you a solution in the worst case. All right, so going back to the algorithm, we do the same thing. We construct a graph. Here, every edge in the graph means that the LCS is large. So for a fixed lambda, if the LCS is larger than lambda L, we assume there's an edge. We find an edge. We discover the neighbors for the 2 endpoints. Now, we would like to imply by birthday triangle inequality that the LCS between left windows and right windows is larger than lambda cube L. The problem is, unlike edit distance, you can't just close your eyes and report all the edges, because birthday triangle inequality sometimes works, sometimes doesn't work. Before reporting, you have to verify. But you don't want to compute the LCS from scratch, because if you do that, the runtime is going to be quadratic. In order to verify, we keep the solution. So in addition to computing the solution for the windows, we also keep the matching. When you want to verify whether you have the solution, a birthday triangle inequality applies to a pair or not, you take the intersection. If the size of the intersection is large, then you assume it applies. If it's small, then it doesn't apply. So instead of spending quadratic time for finding a solution, you spend linear time. So still the runtime is subquadratic. But the issue that comes up is it could be the case that the LCS between these 2 is large, but when we take the intersection, we don't find a large solution. So it could very well be the case that the LCS between all the left windows and all the right windows is large, but when we take the intersection, we don't find anything. The second issue is that how do we guarantee that we discover a lot of edges? Because if we don't discover a lot of edges, then the amortized runtime is not going to be small. So this part is technically challenging. I will just say this. We want to prove that if the graph is dense, this algorithm discovers almost all of the edges. It's already non-trivial to prove that if the graph is complete, our algorithm discovers a single edge. So when you prove this, then you get a solution for LCS. Now I can tell you what the approximation factor is. If the solution size is lambda n, then our approximation factor is lambda squared. So if, for example, lambda is constant, we get constant approximation. One question that many people ask is, why can't we just output n and be sure that we are within lambda of the optimal solution? We don't want to do that because if you overestimate the solution, you're giving an invalid solution. If I ask you to give me the matching, you can't because it doesn't exist. Our solution gives our algorithm gives a solution of lambda cube n, and if you ask me to give you the matching, I can actually give you the matching. Why is this a dual for edit distance? Because we can actually use it for edit distance, and it gives us a better bound. Suppose edit distance is 0.1 n, previous work gives you 0.3 n. You can imply that LCS is 0.9 n. Our solution gives you this, and then edit distance is bounded by 0.271. So we improved the previous work a little bit. One last slide. I mentioned in the beginning that LIS is a special case of LCS. We can solve in linear time. We give a sublinear time solution for LIS. The approximation factor is lambda cube instead of lambda squared. And the technique is completely different. Instead of triangle inequality, we use iterative subsampling. Finally, a bunch of open questions. For edit distance, the big question is, can we get 1 plus epsilon approximation in near linear time? Perhaps before trying to answer this question, there are two easier questions that we can start with, whether we can get constant approximation in linear time or 1 plus epsilon approximation in subquadratic time. For LCS, there's a great question, can we get subpolynomial approximation in subquadratic time? The same question we can ask for LIS. Can we get subpolynomial approximation in truly sublinear time? One thing to note for LIS is that if the solution size is small, like constant, you have to spend time n. So this solution is open for larger LISs. And that's it.
Any questions? Yes?
You mentioned the edit distance result of Grover version of the other.
Grover's, yes.
How was the time improvement? Was it almost linear then? Or?
No, the time was truly subquadratic.
It's still quadratic.
Say that again?
It was still it was not almost linear, I guess?
No, it was not almost linear. So the quantum solution was before the classic solution. Yeah, so they give a subquadratic solution, and then comes a classic solution for it. So the runtime is pretty close to n to the 1.7, I guess. Still, we don't know how to do that in linear time. That's a great question.
Any other questions? Let's thank the speaker again.